I'm really glad to be here. Today I'm going to talk about some new results from Wolfgang Ketterle's group. So our topic will be spin-orbit coupling and spin textures in optical superlattices. So it will be a little bit from the different from the topics of the workshop, but yeah. So we have another new states of matter in the end of the talk. So it will be somewhat connected. Yeah, I'll talk about in the talk. So the outline of my talk is, first I will have a very general discussion on the spin-orbit coupling and its progress in the cold-damping field. And the second, then I will talk about our schemes and how we realize the spin-orbit coupling in the optical superlattices. And in the end, I will talk about to realize many-body Hamiltonian in the spin-orbit coupling scheme, which includes like very exciting phases, different new phases like the stripe phase. So, so just a very general discussion on the spin-orbit coupling. So spin-orbit coupling has been playing a role, important role in many different fields. So in our field, in the internal structure of the atoms, we have spin-orbit coupling, and it contributes to our fine structure splitting, and it modified our internal structure of our atoms. In a condensed matter system, the spin-orbit coupling is even more interesting because it can give like many new and exciting phases and phenomena like the topological insulator, quantum Hall, anomalous Hall effects, and topological superconductor. I won't go into details about it because I'm not in this field. So yeah, since the spin-orbit coupling has been so interesting and it raises so many interests, so in the cold atoms field, we are also trying to do the spin-orbit coupling. And fortunately, it has already been done, many years ago. So the basic scheme of the spin-orbit coupling for the cold atom system is, so first we need to pick the spin degree of freedom for our atoms. So the general choice is just to use the internal states, like the Zeeman states of the atoms, and use these internal states as the pseudo spin degrees of freedom. So how do we implement the spin-orbit coupling? So the general idea of spin-orbit coupling is we have the link between the spin degrees of freedom and also the momentum of the atom itself. So the one idea is just if we somehow flip the spin, and at the same time when we are flipping the spin, we also give a momentum transfer to the system, then sort of we can imagine we will have a coupling between our spin degrees of freedom and also the center of mass motion of the atoms. So that is exactly what the conventional schemes do. So in a conventional scheme, so we're taking the two Zeeman levels as the pseudo spin of the system, and also we have the two photon Raman transitions to connect this to pseudo spins. And because we can arrange the geometry of the Raman beams, we can also provide a non-zero momentum transfer to this system during this to the atoms during this spin flipping process. So if we write down the Hamiltonian, we can easily get a Hamiltonian like this. So we have the non-trivial part is we have a non-diagonal term which also reflects the spin flipping process and also momentum transfer to the system. So if we do some rotating of the frame, we can demonstrate that this is equivalent to probably the simplest scheme of the simplest Hamiltonian of the spin coupling we have. That's the one-dimensional spin orbital coupling with equal contribution from the Rashba and the Dresser-Hales coupling. And this Hamiltonian will give us a new dispersion relationship. So the general feature is we will have, when the spin-orbit coupling is sort of weak, we will have a two degenerate ground state. And if we keep increasing the coupling, the coupling itself, we can imagine will bring a gap when the two dispersions crossing. If we keep increasing the coupling strength between this in our spin-orbit coupling scheme, it will eventually the gap will be too large. It will be so large that there's only a single minimum ground state in the system. So this scheme has already been implemented for many years, including the original implementation from Ian Spielman's group. and for the bosonic rubidium-87, and also after that, very quickly we have the implementation to the fermionic system, like in the lithium-6, like here has done in MIT. However, during this scheme, there's a sort of a fundamental limitation to the system. So because we're using the two Zeeman levels as the pseudo-spin, as long as we want to flip the spin, we sort of have to talk to the state that with different orbital momentum, which means that, say, if we start with the ground state with S with the orbital number, like orbital number at S, then if we want to talk to another state, also has in the ground state with the orbital S, so we have to go through the P states in the atoms, which means that if we just want to do the two photon transition, we inevitably has to talk to all the P states in our state, and they cancel each other, and which gives us a fundamental limit that we are not able to detune our laser too far from the excited states. So if we're not able to detune too far from our excited states, which means that we will be suffering from the many severe heating problems during the spin flipping process, and that is that's the basic limitation that limits the lifetime of all this system for alkali atoms, and especially the problem is getting more and more severe if we're going to the lighter and the lighter atoms. So for the lithium-6, basically the lifetime is already very, very, very short. So we have to do some very quick physics. So are there other ways to like sort of go around this problem? So there are. So one is, okay, so we just go, so we have the problem for alkali atoms, so we just don't do the spin recoupling with alkali atoms. That is what has been done with dysprosium recently. The thing about the dysprosium is that in the ground state of the dysprosium, there are already states that has different different angular momentum, so we can couple them without the near detuned light. Another way is totally sort of a new direction, that is, if we just abandon the internal structure of the atoms at all, and we just use the sort of center of mass motion, or we use the orbital degrees of freedom as our pseudospin to implement the spin-orbit coupling. So this already, there are also some early works done by the Peter Engels in the group, in which he used the S band and also the P band in the optical lattices as the pseudospin. But a drawback of this setup is that the interaction, there will be collisional problem between the S states and the P states. So the lifetime is sort of still limited by the collision between these two, between the atoms in the S state and in the S band and also the P band. And the part is the wave function overlap between the S states and the P states are not tunable. So there's no other way around about this heating problem. So based on these concerns, we propose and implement a new scheme to implement the spin-orbit coupling. So to understand the scheme, it's better. It will be cleaner to go from just a single double well potential. So say if we have a double well potential here, and the two wells has an offset energy delta, and there's a better tunneling there's a J tunneling between the atoms in the two wells. So this is based on our system. And say if we're using the two wells, the left and right wells as the pseudospin degrees of freedom, and we just say that if the atoms are at the left well, we call it a spin down. If the atoms are in the right well, we call it a spin up. And we still use the two Raman beams to couple the atoms from the left to the right, which means that we basically use the Raman beams to transfer the atoms from the left well to the right well, or we can also transfer the atoms from the right well to the left well at the same time. So this is sort of the spin flipping process in our scheme. So if we arrange our geometry of the two Raman beams, we can achieve that when we're transferring the atoms from one well to the other, we can give a non-zero momentum kick along a certain direction. And that is the fundamental idea of the spin-orbit coupling. So we're expecting that in this scheme, there's a chance we can implement the spin-orbit coupling Hamiltonian in our system. Yeah. And more details about our system is, so we use left and right well as the pseudo-spin. We use the two-photon Raman process to transfer the atoms from the left well to the right well. And another thing that's important thing you need to mention that our scheme is arranged so that one of the Raman beam is along the double well direction. The other Raman beam is perpendicular to the double well direction, which is as denoted by the y direction in the system. So we can imagine when atoms were transferred from left to the right, it will get a momentum kick along the y direction. And when they transfer it back, it will get also along the y direction, but with the opposite momentum transfer. So that is the basic idea of the spin-orbit coupling in our scheme. And we can also prove that in our scheme, our Hamiltonian is exactly the same as the one-dimensional spin-orbit coupling Hamiltonian with the equal contribution from Rashba and the Dresser-Haus spin-orbit coupling terms. So what's the merits of our scheme? So first, we don't need to talk to the. We still have to talk, but we don't need to use the internal degrees of freedom as the pseudo spin, which means to implement or to achieve this flipping process, we actually don't need near resonant light. We can use any very far detuned of resonant light. So this is supposed to, if we go off resonant by a lot, we can suppose that we don't have a severe heating problem in our system. And another thing is because the internal degrees of freedom is not playing an important role here, this scheme we can imagine this scheme can be generalized to different atoms, including fermions and like bosons, and doesn't depend on how heavy, like the mass of the atoms and the internal degrees of freedom. And also another a very good part about our scheme is that our inter-pseudo-spin interaction is tunable. So the way to see it is, so in our scheme, the inter-pseudo-spin interaction is basically the wave function overlap between the atoms in the left well and in the right well. And this overlap, it depends on the parameter J, the tunneling between the two wells, and also it depends on the offset of the two wells, which in principle can be tuned very low because the leaking, because it basically depends on this small satellite leaking part of the atoms from one spin state to the other spin state. So we can imagine that if we just change the parameters, we can tune the interaction between these two pseudo-spin states. This will give us control on the lifetime. First, of course, on the lifetime of our scheme, because our lifetime is majorly limited by the inter-atomic collisions. The other part is this tunability gives us a control actually on the many-body, on the many-body phase diagram of the many-body spin-orbit coupling Hamiltonian, which I will go into the details later. Okay, so after a lot of theoretical work, we should go into the lab and see what's going to happen. So now the big difference is instead of using the internal degrees of freedom, we're using the center of mass, which we can imagine using the center of mass could be problematic in some sense, because in a conventional scheme where the internal degrees of freedom are used, the splitting between the two spin states are on the order of megahertz, and the recoil energy of the system of the atoms are several kilohertz, which are very, very far away from each other. But in our system, the energy difference between the two spin states is only on the order of delta, which is only several recoil energies in our system. So this will bring some issues in our experimental implementation. So a way to see this is, so say now we have only a single condensate sitting there, and we put in the two Raman beams. So if we put in the two Raman beams, they're just a moving lattice. We can imagine the Raman beams are just a moving lattice moving across the BEC itself. And what does this moving lattice do? So we can imagine if there's a lattice moving along the atoms, we can imagine it will imprint a density modulation on the BEC itself. So this is fully captured by the process shown to the right. So we have actually three different processes here. So the first process is the process 1 and process 2 describe the imprinting of the density modulation on the BEC. So the story is if there's a BEC sitting there and our detuning of the two Raman beams are not far from say the bandwidth or the recoil energy of this system, we can imagine there will be a so-called on-site modulation on these atoms, which is there will be rotating terms, and there will also be a counter-rotating terms, which is just the same a condensate staying within the left well, still staying within its left wells, but there is a modulation imprinted by the Raman lattice. And the process number 3 is the process we want. It's a spin-orbit coupling term, which means that we are transferring atoms from the one state to the other state to the sort of doing the spin flipping. So yeah, as mentioned here. So however, if there are any way we can distinguish these two processes, because the question is not actually hard to answer, because in the beginning, when we were doing experiments, we haven't thought about this on-site coupling or this with the modulation within the original wells without any spin flipping. So so the point of how we distinguish these two terms is that we notice that for the atoms, if our Raman beams, the detuning of the Raman beams matches the detuning of the two wells, so therefore we're on resonance with the spin flipping, we're expecting a resonant feature like transferring the atoms from the one spin to the other spin state. And however, because this detuning is usually several recoil energy, which is still much larger than the recoil energy of the atoms, we can expecting this counter-rotating on-site term and a rotating on-site term and a counter-rotating on-site term roughly have the same amplitude, though they appear at a difference. They're acquiring opposite momentum transfer, but the amplitude the amplitude of these two terms are roughly the same. So the main signature we're looking for is that when we're scanning the Raman detuning, is there a moment that we can get a resonant transfer of atom towards one side above the symmetric on-site coupling term that will appear all the time? So another...
Will the on-site coupling term produce heating?
Yes, that's possible, but we haven't observed any heating from the on-site terms. Yeah, but that is totally possible. Yeah. So if we go into some math, so we demonstrate all these terms. So we have the original BEC sitting in the for example, in the left well, and we have the two on-site terms, which means that we don't flip the spin, but we give the momentum transfer. and they're symmetric on the both sides with the opposite momentum transfer. And then when we're scanning the Raman detuning, we're expecting an unresonant spin flipping process, which gives a momentum transfer, but also transfer the population from one well to the other well. And we have the similar process for the atoms started from the spin up, like our higher states. So we have the bare BC, we have the two on-site terms, and we also have the spin orbital coupling term. And we notice that for these two processes, the spin orbital coupling term will acquire opposite momentum transfer from the Raman beams. And then after we understand all this double well, all our spin orbital coupling scheme in a double well, we go into the experimental scheme in which we realize the system in a superlattice. So what's the difference between a 1D? So our system is a purely 1D superlattice, or say quasi 1D. We have no confinement, or just a harmonic confinement along the other two directions, perpendicular to the lattice. So what is the difference between the superlattice and the double well? So superlattice is basically, we can take it as a chain of double wells which still have coherence between the different double wells. And how does this modify our system? So our spin down and spin up states used to be the atom sitting in the left well and the atom sitting in the right well. But in the superlattice, we have to take everything into the band structure. And actually, it will change our system, and our spin down atom pseudo spin down state turns out to be the zero momentum quasi momentum state in the ground band, and our pseudo spin up state turns out to be the pi q equals like quasi momentum equals pi over d. D is the lattice spacing, pi over d states in the first excited band. So how will it change our physics? And actually, the changing from the double well potential to the superlattice potential helps us in basically two ways. The first is we can sort of taking advantage of this interference between the different double wells. So we can imagine that now if we're in a band, in a quasi-momentum equals zero state, we will have a pattern. If we do the time of flight, we can have a diffraction pattern for our clouds. Once, if we're having a state in a quasi-momentum equals pi over d state, we can expect another time of flight diffraction pattern. But these two patterns will be totally orthogonal to each other, which means that if we just do a time of flight and take a single image, time of flight image of a system, we can tell which atoms are in the q equals pi over d state, and which atoms are in q equals zero state without actually doing any band mapping techniques. And also, this is describe what I just said. So for the spin down state, we have the q equals zero state, and we're just expecting the normal diffraction pattern with the peak centered at q equals zero. But for the spin up states, it's in the q equals pi over d state. So we're expecting a momentum shift of the interference pattern, and also the distribution will change to the distribution that the q equals pi over d state has. So we can imagine if these two states are like added together, we can still tell which is which. We can count the number of atoms in the q equals pi over d state, and we can also count the atom number in the q equals zero state, which can directly tell us which atoms are in the spin up state and which atoms in the spin down state. Okay, so how does superlattice affected the signal we're looking for? So we just described that the signal we're looking for is imbalance, population imbalance between population imbalance between the two on the state with the two opposite momentum transition, and And how will the superlattice change our system? Actually, it will be very simple. So we basically just have the single condensate, and we superimpose the Bragg scattering, the Bragg peaks from our superlattice. So eventually, the signal we're looking for is we have, say, for the atoms started with spin down state, we have this center line of atoms, which are just the original atoms, and after we put in the Raman beams and changing the detuning of the two Raman beams, we can definitely see the two lines here corresponding to the counter-rotating and the rotating terms. And we're expecting when we're scanning the Raman detuning, there will be a resonant frequency. We have a population enhancement on one of each line, on one of the lines. It depends on which process we have, and it depends on which spin states we started with. So, for example, if we started with a spin down state, we were expecting we are expecting a population enhancement in the upper line, but if we started with the spin up state, we're expecting a population enhancement in the bottom line, and that is okay. So that is actually exactly what we observed. So these are just the two bare spin down and spin up states, and now we started putting in the Raman beams. So the color scale is it's a little bit. So we can see that there are peaks appearing as we described at the two extra lines due to the Raman coupling, which is a combination of counter-rotating on-site coupling and the spin-orbital coupling. And when we are Raman detuning our off resonance, we can see that the population in the top line and the bottom line are symmetric. They have exactly the same population. However, when we're scanning the Raman detuning and when it's hitting on the spin-orbital coupling resonance, which means we're hitting on the resonance that's transferring the atom from the left to the right, we can see that the population is enhanced on the top line of the system. And similarly, if we started with the spin-up state, when the Raman detuning are off resonance, we can see the symmetric population distribution in the top and the bottom line. But after once we got the resonance, we can see that the population is enhanced in the bottom line instead of the top line, which is the opposite as the case when we are starting with the spin down state. So now we can see that we already observe some effects of spin-orbital coupling. So now to quantify all this population imbalance that we have to, and figure out where the resonance is, we have to do some more careful work. So we quantify this system by calculating the population imbalance between the atoms in the top line and the atoms in the bottom line. And we just plot it with the Raman detuning, and we can see that there are clearly two resonant peaks, and the peaks has different amplitude, like different signs, which means that they're transferring in a different process and in a different direction. And another feature we can see is that these two peaks are separated by roughly in this diagram is roughly in the roughly free recoils energy of the atoms, which is roughly 7.6 kilohertz for our system. We are using the sodium. So this can be explained by just simply the energy conservation in our system, because when we are transferring, depending on which spin state we started with, when we are transferring atoms, we can either provide the extra transverse kinetic energy with our Raman beams, or on the other way, the offset the energy that's released when the atoms are transferring from the spin up to the spin down state will, together with the Raman detuning, will provide this extra transverse kinetic energy. And also from the inside, we can show that this offset between the two peaks are almost a constant along across a very wide range of different resonances. Okay, So until now, we have demonstrated that for our spin, we have proposed a new scheme for doing spin-over coupling. And we have demonstrated the single particle physics with it. And another thing before I move on, since I only have 5 minutes, I will just skip very quickly. So another thing interesting we discovered during experiments is the states that with the equal population of the states with spin down and spin up. So as the cartoon shows, if we have the spin down, we have only this. As spin up, we have this. And if we have spin up and spin down, we simply have all the patterns together. But it could be more interesting if we take a look at this wave function over here. So the wave function, I will be focusing on the third state, which is more interesting. So for the wave function, we can see that if now, so this n is the site index. Let's say it's from the site n. So if we take the spin down and spin up, if we use the picture of the Bloch sphere, this is just a corresponds to the spin state along the x direction. It's not in the z direction anymore. And if we take the site, next to it, it's actually because there's a pi phase due to the band, due to that the spin up state in the second band. We actually have the pseudo spin actually flipped in the x direction. And then if we go to the next side, we actually get it flipped back. And this can be shown by calculating the expected value along the spin sigma x and sigma y. We can show that this is actually spontaneously forming a sort of antiferromagnetic pseudo-spin ordering here. And okay, so if there's a spin, the more interesting thing is actually there will be a corresponding density modulation in our system. So the way to see it is, let's go back to the original setup. And we see that there is a tiny satellite here, which means that if we superpose these two wave functions together, they will change the wave function in each site, and it will correspondingly change the density in each site. So if added together, and we just calculate the wave functions, the projection of wave function in the left well in the site n and the right well in the site n, we can actually get a density modulation like this, which means, so the solid circle means the little bit higher density, and the hollow circle means the little bit less density. So we will spontaneously get the density modulation, which has twice the periodicity of the original lattice. This is very interesting because this thing just spontaneously breaks the translational symmetry of the original lattice, and it also has, because it's a BEC, it also definitely breaks the U1 symmetry, which is it actually fulfills some definition of the supersolids. But yeah, so the way to detect this density modulation is actually we just actually did it by shining the Bragg beam and find a certain Bragg scattering angle. So Bragg scattering basically is the coherent, it's the elastic light scattering, and if there's a periodicity in the system that you shine light on, we're expecting enhancement in the certain angles of the Bragg reflected beam, and the angle will reflect the periodicity in the system. And actually, we did the Bragg experiment with this, with our with this system with equal population of the two states, and we actually saw the Bragg signal that's along the direction that reveals this doubling frequency in the system, periodicity in the system. Okay, so all the above I described about the single particle physics, and I'll just quickly go to the, since I don't have time, so I'll just quickly go to the many-body physics. So in the many-body physics, how are we expecting to change our Hamiltonian? So we will basically have another term which describes the interactions. So in our system, there are three parts of interactions. One is between spin-down interaction and the interaction between spin-up states, and the interaction between the spin-down and the spin-up states. So how will it change our scheme? How will it change the states we observe? So we can start it from this. So say if we have a single particle system, there's nothing, like no interaction there. Once we have two degenerate ground states and our BC is populated there, we can just imagine that these two states just stay there and they interfere with each other. And if we increase our spin-over coupling, eventually we will go to a single minimum dispersion relation, where all the atoms will condensate in the single minimum. So once we have the interaction between the atoms, the difference will be that, say, if we have the interference between the two, ground states, we can imagine there will be a density modulation just between the interference effect, because we're interfering two states with different momentum. So this density modulation in the mean field regime will increase your energy a little bit. So we can imagine that if this effect is too strong, the system won't like to stay in the spin mixed state. It will try to demix, and these two spin states will try to separate from each other, which we call the demix phase, or by some literature called the magnetized phase, which means we have non-zero magnetization in the system. To be more careful, we can actually so there is a calculation on the phase diagram which shows the stripe phase, which is the superposition, like coherent superposition of the two ground state and basically the miscible state. And we have the separate phase state, and we have the single minimum phase. The stripe phase is very interesting. It's interesting because it breaks the U1 symmetry and also the translational symmetry of the system spontaneously, which is type of the supersolid. So since the stripe phase is so interesting, like a lot of group has definitely done experiments on it. So the first experiment is definitely by Ian Spielman. So they basically ramp the system, prepare the system in the stripe phase, but they observe that the two states are miscible, but actually they don't have any direct detection of the stripes. And also there are other groups which measure the excitation of the spin-orbit coupling Hamiltonian. They can show that there is a transition point in the changing of the excitation, but still there's no direct detection of the stripe phase. So the reason for the detecting of why it's hard to detect the stripe phase is that because for the rubidium atoms, the intraspin interaction and the interspin interaction are so close to each other, which means that the stable window for the detecting the stripe phase to exist and the contrast that they can get from the stripes are really, really small. But for us, I'll just go very quickly. But for us, because I mentioned before, we can tune the interaction between the two spin states by just tuning the wave function overlap. And this guy can be very, very small. So for the rubidium system, maybe the spin down, spin up, spin and spin interspin interaction can be roughly 99% or even larger than the close to percent of the intraspin interaction. But for our case, we can get it to even less than 1% of the intraspin interaction, which is another extreme of the system. So actually, for our system, we can imagine that the stripe phase is actually a favorable phase for us. So if we calculate the phase diagram following the same method for the rubidium, we can get that this is our regime for the stripe phase compared with this tiny little bit. So in one word, our system has the ability to create a very strong interspin and intraspin interaction imbalance. So which means that it will be very favorable for the stripe phase detection. So what will the stripe phase be like in our system? If we started with the spin up, spin down, and spin up, and we interfere them together, we can expecting stripes along the transverse direction for our system. And this periodicity, we don't have single-side resolution again, but we can detect this periodicity by using the Bragg scattering of the system. So hopefully, we can eventually, if we prepare the 50-50 mixture of the system and we put it at the put in the Raman coupling and put in the Bragg scattering, we're expecting some. We can expect some Bragg scattering at some certain angles, which reveals the density in the system. Okay, so conclusion, I'll just skip. But I'll thanks for all this work is done by all the collaborators in the lab, and thank you for your attention. Yeah.
Questions?
Can you comment on heating issues? I think the question is how if I put fermion in the systems and in the future, so that would be it's a very well, if it's just no heat or very little heating, then this would be an excellent.
Yeah.
Case for
Yeah. So. Yeah, so for us, because we're off-resonant and far detuned, so we definitely don't worry about the heating from the Raman beams.
Experimentally, you just don't see
Yeah.
much heating.
So experimentally, we saw heating when we ramp up the Raman beam to very strong intensity, but we believe it's just technical issues now. So physically, we don't see very strong heating. Yeah.
One thing I didn't understand was how you map the two-body interaction onto this double well scenario. It seems like you now in momentum space you have kind of non-local potentials or something. I don't know. I mean, you just wrote a Lagrangian with a coupling constant, which would be the same form if you had zero range interactions, but it's not obvious to me that that's really justified.
So this is the means. Yeah. So the interaction in our system is on-site interaction. So it is the contact interaction. So by saying we can tune the interaction, I mean that if we consider the atoms in the left and the right, this elastic collisional interaction will just comes from this atom. They have a little bit satellite over there, and this atom is in the spin down state will have a satellite over there. So if we consider only the contact elastic collisional interaction, only this part of wave function overlap will contribute to this sort of interaction.
So it seems like, yeah, it's an exponential potential or something like that.
Yes. So we tune the interaction by tuning the wave function overlap. Basically, we tune the density terms in the interaction terms. So, but all the interactions are still contact interaction.
That's why you can tune a lot.
Yeah, that's why we can tune a lot. So yeah, so in other words, we're not tuning the scattering length, we're tuning the density, the effective density for the interaction.
Okay, anything else? I guess not. Well, thanks again.
Sure.